And Jennifer is the Fletcher Jones professor and chair of the Department of Computer Science at Stanford University. Her research interests are with data management systems of all non-traditional aspects of data management systems. She is a member of the National Academy of Engineering and the American Academy of Art and Sciences, and he has won many honors and awards. And today, she's going to talk about a system for provenance and data, which they developed at Stanford, and it is called Panda. And Jennifer.
Okay, thank you very much. I guess I'll introduce my former student, Anish, who's on the screen here at the front. Hi, Anish. We're all looking at you. Anish has worked at Google for a while. He was my PhD student. He's now working in New York. Okay, so thank you, Photo, for the introduction, and thank you for having me today. I like talks that are interactive, so at any time you can ask me a question, even here on the title slide, although I doubt there's much to ask. Panda stands for Provenance and Data, and so I'm just going to be talking generally about work we've been doing in the area of provenance recently. So I'm going to start with an example. It's obviously a fabricated example, just to motivate the use of provenance in a setting of what we call data-oriented workflows. So let's imagine that we have a workflow where we're going to take in some customer information and some buying information catalog and predict what customers are going to buy or what the demand for our products are going to be. So we'll start out with some customer lists. And they might be of varying types of customer lists. We might have gotten them from multiple places. So the first thing we'll do is send those customer lists through some kind of deduplication operator. After the deduplication, we're going to canonicalize the lists in some form, and we're going to take the ones that look like they came from Europe and canonicalize them in one way. If it looks like they came from the US, we'll do it another way. This is just to demonstrate different shape of workflows. Once they're in this canonical form, we'll union them back together. That's when we'll throw in information about our catalog and some of the buying patterns that we've seen in order to make predictions about what the customers from those customer lists are going to buy. We'll aggregate together our predictions to determine what type of sales we'll see. Okay? And after we run this on our customer list, we discover that we expect to sell a lot of cowboy hats. Okay, so I'm the analyst. I've done this, run this workflow, and I'm pretty surprised that I'm going to sell a lot of cowboy hats because that's not my customer profile. That's not my demographic. So now this is where provenance is going to come into play. If I just ran the workflow, I finished it, and I have my output data and everything's thrown away, I can't really figure out anything about why I have cowboy hats. So now I'm going to use provenance to trace backwards and see what happened. So I will do backward tracing. I'll send that cowboy hat prediction back one step, so back through my aggregator, and I'll discover, this is obviously there would be a large number in reality, but I discover I have 3 customers, which is a lot, who want to buy cowboy hats, who I predict will buy cowboy hats with a relatively high probability. Now, that still seems odd to me because I really didn't think that I had a lot of people from the South, for example, who might buy cowboy hats, so I have to keep tracing backwards. Again, hopefully I capture the provenance in order to do that. So I go back and I find that these 3 customers are from Paris, Texas. So some of you can probably already see what's going to happen. If I keep tracing backwards, I will send it back, and I'll discover that the data that I'm looking at went through that the USA canonicalizer there. And the data actually, this is what it looked like before it went through there. So I'm starting to get suspicious that maybe I sent the data through the wrong way through my workflow. And I did that by tracing back with provenance. So I go back entirely to find out where those customers came from. Obviously, those customers were from Paris, France. And so they came from this customer list. So I can either fix that customer list to say that these people are from Paris, France, or I could fix this splitter, which sent them accidentally through the USA, and that's what added Paris, Texas to the data. Okay? Everybody follow that? Okay. So I've used provenance to figure out what went wrong. This is the use of provenance for debugging. And after I've fixed the data, or fixed either the customer list or the splitter, then I can send the data back through. And so now this is using forward propagation. We'll also see how provenance can be used for that. So I send the data back through. This time it goes through Europe, the Europe canonicalizer instead of the US, and instead of making it Paris, Texas, it makes it Paris, France, and then we keep going, goes back through, and out comes a beret instead of a cowboy hat. Okay, so that's just a toy motivating example of how we can use provenance to explore what happened when we sent data through a workflow, and that's sort of the whole topic of the talk. Okay, so let's go back and talk about provenance a little bit. I'm going to give you a definition, but different people have definitions. Very broadly, provenance is where data came from, how it was, where it came from in the first place, how it was derived, how we manipulated it, combined it, and so on, and also potentially how it's evolved over time. And there's plenty of uses of provenance, and probably everybody sitting here has some use of provenance in their mind, probably a bunch of different ones. Broadly speaking, you can use provenance for explanation, so drilling down on data. If you have a bunch of derived data, you want to find the source of the data, it's a deeper understanding of how the data was derived. Debugging is a particularly common use, as in the example that I showed you, where we have data that's been processed by a complex workflow. It looks wrong. We want to find out, why is it wrong? Is it because we made a mistake in the workflow itself? Is it because the original data had bugs in it? We can also use provenance to figure out how errors propagate. So if we find an error, if you, say, get some derived data, you go back to the source data, you find an error, provenance can help you find out exactly how that error spread through other data, other processing that you did on the same data. And provenance can be used for auditing. And it can also be used for recomputation. So provenance is the key, in some sense, to doing incremental processing in this environment. Okay? Application domains, well, sales prediction workflows, but again, that was a toy example. I think scientific data workflows are one of the original drivers for provenance. The scientists were recognized decades ago that they needed provenance. They do a lot of gathering of raw data and then a lot of processing on it, layers and layers of processing. They look at the outcome. It doesn't look right. They need to find out what happened, where the source of that was. And that also includes, by the way, human-curated data. And I made this slide before crowdsourcing became popular, but humans getting involved in the workflow really complicates the problem of provenance, of course. And again, evolving versions of data is pretty relevant for scientists. But pretty much any analytical pipeline can make use of provenance. ETL processes, I know information extraction pipelines are used here and in other companies. So that's just some examples. Okay. Now, let me say third time's a charm. First of all, one thing that may be going through your mind is, isn't provenance the same thing as lineage? So people talk about lineage a lot. Now I'm talking to you about provenance. And for those who know some of the work I've done at Stanford over the last couple decades, you might ask, gee, haven't you worked on this problem before? Okay, so first of all, yeah, provenance is pretty much the same as lineage. Some people think of lineage as maybe more smaller scale or something, but let's just call those synonyms, provenance and lineage. And provenance seems to be the term people feel like using these days. And have I worked on it before? Absolutely. Actually, this is the third time I've visited the provenance problem. So the first, and that's why third time's a charm, maybe. Okay, so the first time I worked on it was in a data warehousing project. This was long ago, I don't know, 15 years ago, maybe something like that. So in that project, this was back when data warehousing was kind of a new idea. The whole idea of having small operational data sources and then bringing that data into a big warehouse for analysis was, at some point in time, relatively new. So we did research in that area, and the research we did that had to do with provenance or lineage was simply if you define your big warehouse as a relational view over the little relational operational sources, then you might be interested in your warehouse when you're looking at some data of finding the origins of the data in the operational sources. And there were some actually quite interesting problems that we worked on there. We worked on, caching issues. What exactly do you have to cache in the warehouse so you can go back to the original sources and so on. So various system issues, also some formal foundations. We also looked a little bit at that time at ETL pipelines, so extract, transform, load pipelines, because those were used in warehousing as well. Okay, so that was a PhD thesis or two quite a while ago. Much more recently, but still a while ago, was the TRIO project. And the TRIO project was called TRIO because it had three components all working together in one system: data, uncertainty, and lineage. And those three, the uncertainty and lineage sort of looked orthogonal to each other when we started, and I'm still not completely sure why I started a project with those two components, but it became very clear from a technical perspective, it must have just been some intuition or something or random luck, that actually lineage is very important when you're trying to manage uncertain data. Because when you bring together data that's uncertain, if you want to evaluate the certainty or the confidence of that data, you actually have to go back and look at the confidence of where it came from. And this is not a talk about TRIO, but in that project, but I'm happy to talk about it offline, but in that project we had a pretty narrow definition of what lineage or provenance was, but that definition, that use of lineage was very key to the system we built for managing uncertain data. But it was mostly in support of uncertainty. So that was time one, then there was time two. Okay, so now here's the third time's a charm, sort of, which is the Panda project, and that's very recent, although we're kind of winding down or have wound down. But that's what I'm going to tell you about today. In this project, we've been focusing particularly on these things called data-oriented workflows, not on uncertain data, not on data warehouses, like the example I showed you, but I'll be a little more formal about it. And then we tried to explore some of the sort of maybe more fundamental aspects of provenance, fine-grained provenance versus coarse-grained provenance. Provenance defined at a logical level versus a physical level. What to do when some of the transformations in your workflow have a known structure, you know what they're doing. What to do when you don't know what they're doing. All you see is the input data and the output data. So that's the types of things that we explored in the most recent foray into this area. And we worked on foundations, we worked on algorithms, we built a system, a couple of systems, 3 systems actually, and I'll touch on all of those today. Okay, but actually I'm going to make a bold statement about provenance, which is no time is ever going to be a charm. Okay? I actually have a fairly strong opinion about the area of data provenance, which is that you're never going to solve it. It's an unsolvable problem. Okay? There's never going to be a general framework. So I've tried it 3 times. I tried one area, another. I don't think there's ever going to be a solution. It's an impossible dream. So if you want to leave now, anybody want to go? Nope. Okay. So it is an impossible dream. As I look at the different applications for provenance, different applications need different things. So I've had so many people come to me and say, I need provenance. And I say, well, what do you think provenance is? And every time they say something different. So I think that the common denominator is actually quite small. Okay? So actually, that's fine for academics. It doesn't bother me very much. There's lots of relevant research to do. As you can see, I've had 3 waves of PhD theses in this area, so no problem. That's great. But it is more of a problem if somebody thinks they're going to build the provenance system, because I actually personally think they're not going to. So, again, you can leave if you want. I've said exactly the same thing about another research area for the last 2 decades. Exactly the same. I could just replace the word provenance with something else. Does anybody know what it is? I knew Alone would know. Yes? Data integration. He says the data integration problem will never be solved. Thank you. Yep. I have given a variety of talks where I say I really don't think data integration is ever a solvable problem. The common denominator is just way too small. Everybody's view of what data integration is different from everybody else's. But actually, again, in the academic setting, no problem. Tons of great research to do in data integration. Okay, so that's my introduction. So for the remainder of the talk, I'm going to give some fundamentals. I'm going to talk about capturing provenance, exploiting provenance, some of the actual concrete results we've gotten, and follow-on work. Any questions or discussions at this point in the talk? Okay, looks like we only lost one person who's decided I'm not going to solve his problem. So, yes?
So you say you can't solve the problem in the general.
Right.
Are ways of identifying categories of problems that are actually solvable?
Exactly, yes. And we solved a category way back with our data warehouse, and that category was if you have a relational view of some relational data sources, how do you cache data to make provenance efficient? Great, no problem when you have that. But that's not actually most people's problem, unfortunately. It's a great academic problem, but it's not the main real-world problem. Second time, we used provenance behind the scenes to build an uncertain database. Great, that was actually, provenance was fantastic, but we weren't solving anyone's provenance problem. We were solving their uncertain data problem. And so you'll see, I'm going to tell you some settings where we have some results. but are they actually what people need? Not sure. It's what some people need, but I don't think there's anything that's going to solve even 50% of the provenance problems in one system. Yep. Yes?
So by taking the uncertainty out, taking uncertainty out, are you saying you're less excited about a certain data today than you were 7 years ago?
If I take uncertainty out of trio and I just have data and lineage?
No, you were doing uncertainty and then provenance. Now you're doing only provenance.
Oh, but I'm doing something that's unrelated. In some sense, what this project is going to tell you about is almost unrelated to how lineage was used in the trio system. That was a very specific use where you were running relational queries and keeping pointers to where things came from so that you could resolve confidence values. You're asking if I'm excited about uncertain data? Yeah. Of course. Why wouldn't I be? Uncertain data is everywhere. Uncertain data is a great problem. But I never work on anything for too long, right? So it's time to move on to something new. But uncertain data is an extremely important problem. And actually more solvable than provenance, in my opinion. I think you can sort of build a system that has uncertainty in it that will solve some reasonable fraction of people's problems, where I still feel a single system for provenance is only going to solve, a small fraction. So I think uncertainty is a more contained problem that can be defined and solved in a more contained way. Yes?
You make the distinction of when the bad data is adversarial rather than just random errors?
Do I? No. Not in anything you're going to see. I'm not going to quantify why data is wrong. It's just wrong. Yeah. Okay, so why don't I move forward and tell you a little bit about what we've done. Okay, so for fundamentals, I'm going to define data-oriented workflows. I'm going to give you an extremely simple underlying provenance model. And then I'm going to talk about capturing provenance. And for exploiting provenance, I'm going to talk about different things you do with it, sort of like I showed you, backward tracing, forward propagation. I'll also define refresh. And I'll talk a little bit about ad hoc queries that involve provenance. So that's all introductory material. Then I'll talk about the concrete things that we've done and follow-on work. Okay, so let me define a data-oriented workflow. So data-oriented workflow is a graph, let's make it a directed acyclic graph of what we call processing nodes. Each of those round things is a processing node, and data sets move through on the edges. The reason those are different colors is because some of them might be opaque, some of them we might know exactly what they're doing. So, and I'll talk about that in a little more detail. So a couple things to assume. One thing I'm going to assume, this is a relatively strong assumption, is that we define the workflow statically. So the workflow kind of sits there, and then we send data through in batches. Sometimes there are environments, and this is a good example of, different people need different things. Sometimes there are environments where the workflow is sort of created as the data goes through the workflow. It's more dynamic. But I'm going to assume that this is just a statically defined workflow. Don't assume anything, though, about the data sets or the processing nodes. I'm going to try to be very general about those. So the goal is that when we know something about how data is being processed, we will try to exploit that in provenance, okay? But if we don't know much about what they're doing, we still want to fall back so the whole system kind of works. That's the basic idea. So what kind of things would we know about a processing node? Well, we might know that it's doing a relational operation or some query in a language that we can analyze. We might know that it's monotonic, so that's a little broader property. Monotonic, in case people don't know, if you put in a data set and you get output, then if you put in a superset, you'll get a superset as output. So it's just a nice property, and a lot of times when something's monotonic, you can have better formal foundations. We might know that it's a one-many operator, so when you put one thing in, many things come out, or many-one goes the other way around. We might know that it's a map function or a reduce function, for example. So those are the types of things we would know about our nodes, and the general principle is the more we can say about our nodes, the finer grained we can be about the provenance that we collect. So if we don't know anything about what a node is doing, we put in a big data set, another data set comes out, all we can say is the whole output set came from the whole input set. But if we know sort of more details about what it's doing, then we can make more fine-grained claims about the provenance. And I'll just give you some examples right now from my workflow. So the known relational operators in this workflow are the union operator and the aggregation operator, so those could be written in a relational language. We know that our deduplication operator operator is a many one operator. So I'm going to find copies or near copies of customer records, and I'm going to merge them, so each group that gets merged into a record makes it many one. But it's non-monotonic. If I add more data, I'm not necessarily going to add things to my answer. It might change my answer in unpredictable ways. Okay? The split and the canonicalizing transformations are very simple. They're just 1-1 transformations. They're monotonic, so those are good ones. Maybe the predict one, we don't know what it's doing at all. That might be just completely opaque. Okay? So our idea is to try to get provenance working with these known properties. And I'm going to use a very simple provenance model, extremely simple. It's just going to say that underneath, provenance is just a mapping between input data elements and output data elements. Okay? So that's what I'm going to assume. I'm not always going to know what it is, but that's going to be my underlying model. So that's very simplified in some sense. And this is another example where some of you might say, ooh, that's not what I needed. I needed something completely different. But this is what I'm going to work with, and I'm going to call that data-oriented provenance. And it's sufficient for many purposes. I put most here. Sure, why not? Okay, most of the ones that I think about. Okay, so the idea then is, so now I've defined provenance for you. I've motivated that different transformations have different properties. The idea is that as the data is processed through one of these workflows, somehow those processing nodes are going to provide the provenance along with the output. They're going to have to do something. If they don't do anything, then I just get my output at the end, and I don't have much to do. So broadly speaking, there's two ways of capturing provenance. One is eager and the other is lazy. So eager says as the data moves through one of these processing nodes, I'm going to generate the provenance. Maybe I'm just going to generate physically that mapping between input and output elements. Maybe I'll generate something a little broader, and we'll talk about that. The other possibility is that you have a tracing procedure. So the processing node, and in fact this might not even have to do anything specifically when the data goes through, has a way of tracing data back. It basically has an inverse. Okay? So those are and the inverse then would be, you'd be probably doing most of your work at the time that you're tracing provenance, where eager you're doing most of the work at the time you send the data through the workflow. Okay? All right, so as an example, how provenance might be captured in our workflow, if we look at our relational operators, the union and the aggregation, there's been a lot of work on relational provenance, including that part 1 of the 3 times I've looked at it. So it can be done automatically. You can take SQL and you can automatically generate provenance for most SQL queries. You could do it eagerly, you can do it lazily, both work. Okay? You can take a SQL query and essentially invert it in many cases. Okay? For deduplication, it's kind of an interesting one. So think about these entity resolution algorithms. They go through a big set. They might have sort of complicated things that they do. Eventually, they decide that these different blocks of records represent the same entity, and they merge them. And so it's pretty easy at the time that you are doing a deduplication for most of them to capture which block of records you decided were the same and got merged into a single record. And you can just have like backward pointers or something like that. It would be much harder to do that lazily, to take an output record. It depends on the algorithm, but to take an output record and find the ones that you decided to merge. So this is an example where it's pretty good to do things eagerly. Not that much extra work. Would be hard to invert. The 1-1 transformations are very easy. I mean, it's 1-to-1. Very often there's a key that you can just trace back and everything works well. You can do it eagerly or lazily. And then the prediction, of course, depends entirely on what's going on inside there. The worst case is that for some of these operators or these processing nodes, you don't have fine-grained provenance. But that's kind of a problem because if at some point when you're tracing back, all you can say is the provenance is the entire input set, then you've lost anything useful. Okay? So that's it for capture. I know I'm still kind of general. Any questions at this point? All right, so let's suppose now we've captured provenance. Yeah?
Sorry. So you mentioned the relational operator being, in many cases at least, invertible. But you might use relational operators, for example, to do deduplication.
Yeah, so they're not all invertible. The simple queries are invertible, but there's also plenty of work on how to augment queries to capture what you need. And so you would do that with the deduplication. You can just sort of write out identifiers. There's known ways to capture what you need. Let's put it that way.
You're suggesting in that case, in fact, modifying your output results to actually capture
Often, yes, that if you're doing eager, and for deduplication is a good example where you probably wanted to do it eagerly, then you will modify your processing to write off some information about provenance. Yep. And so it's known for SQL, for most of SQL, for standard SQL queries, it's known how to do it both eagerly and lazily, how to augment the query to write off provenance or to invert the query when it's possible. And there's been a lot of work in that area. Okay, so let's suppose that we have our provenance now. What do we want to do with it? What are the basic operations for provenance? So there's backward tracing and forward tracing. That's what people think of most. So backward tracing is exactly what I showed you. I want to know where that cowboy hat record came from. So I want to trace provenance backwards from the output into the input. Forward tracing is the other direction. And provenance is useful for forward tracing as well. So I have a particular customer and I want to know which sales predictions she had an effect on. So I want to take data here at the front and figure out how it affected things in the back. Okay? Forward propagation says maybe I changed some data at the front and I want to propagate those changes through, but I don't want to rerun the entire workflow. And provenance can be very useful for that. I mentioned that already, for incremental processing. Refresh is kind of a combination of backward tracing and forward propagation. Refresh says, let me look at my output and let me say there's one element that I want to refresh. I want to this isn't a great example, but maybe I want to refresh all the sales predictions for hats. So some small subset. Provenance can be very helpful to refresh just a portion of the workflow. And again, that's basically tracing that data back to its origins, which the origins might have changed, and then propagating the new values through it. I'm going to go into that particular operation in some detail in one setting. You might also want to ask queries that involve provenance, and I'll just give some examples. Just a sort of declarative query says, how many people from each country contributed to the cowboy hat prediction? So now I'm combining queries over the data with queries about the provenance itself. Okay. Other examples, which customer list contributed to the most to the top 100 predicted items? So what are my most valuable customers? Again, combining the data with how the data went through the workflow. For a specific customer list, which items have higher demand than for the entire customer set? So who do I advertise to? Or which customers, this is slightly different. This talks about how things went through the workflow. Which customers have more duplication, the ones that went through USA or the ones that went through Europe, for example? So there's various goals for a query language. You'd like it to be declarative. You'd like to have ad hoc queries, like a database system, combine provenance data and be optimizable. And I'll just say right now, we never got to that. It looks like fun stuff, but we're kind of winding down, and so that's an area that I'm not going to say much more about. Okay? So let me just talk about the concrete results that I am going to tell you about. I'm going to actually give you 3 different settings, and you'll see how they relate. One of them is where we express provenance as predicates, and this is probably the most general way of expressing provenance that I'm going to tell you about today. And the work we did here was actually motivated by looking specifically at that refresh problem, saying I have an output element that might be out of date based on changes to the input. How do I use provenance to trace back and then push those forward? It turns out to be a very hard problem. And so that we're going to use provenance as predicates for that problem, and that drove the first prototype that we built. Then I'm going to talk about logical provenance, and this actually turns out to be a nice way to specify provenance in the settings where it works. Doesn't always work. And that drove the second iteration of our prototype. And the third thing I'm going to talk about is what we call generalized map and reduce workflows. And this is a data-oriented workflow like I showed you, except every node is either a map function or a reduce function. So that's even more specialized. In all cases, we focused on defining the logical foundations, and we focused on the operations of tracing, backward tracing, forward tracing, and so on, and did not work on the ad hoc queries and optimizations. Okay. I will say that what I'm going to talk about goes from most general to least general. Okay, so remember I said that when things, we know very specific things, we can capture fine-grained provenance, and you'll see that. So the predicates are the most expressive provenance language I'm going to talk about. Logical provenance is a little less expressive, and then these generalized map and reduce workflows are the least expressive, but then we can do the most. Okay, so everybody good? Any questions? All right, let's talk about provenance predicates now. And this is a kind of formal model, you'll see. So we're back to our data-oriented workflow with the different colored nodes, and let's look at just one node, and let's talk about what happens at that one node. Then we'll talk about workflows. So we have, we start with our data here. Things go through. At this point, we have some input I to this black node here, and let's suppose that some element came out O. So I is our input, O is our output, and O is one element of our output. Okay? So what I'm going to say in this model is that we're going to have some way of capturing provenance that describes the provenance as a predicate. That predicate is P here. We're going to associate with O a predicate P that allows us to find the provenance of that element in the input. In other words, the provenance of the output is apply that predicate. This is the relational algebra selection operator. Everybody remembers that from college? Hope. We apply that predicate to the input, and that gives us the output. Okay? This is a model. In the general case, we have our whole output. Every output element is going to have associated a predicate that gives us the provenance of that output element. Okay? So the worst case, we can always have a provenance predicate for every output element. The worst case is that that predicate is the predicate true. That says that I really don't know where this output element came from. When I apply the predicate true, I'm going to get the entire input set. So all I can say is that entire input definitely had something to do with this output. I can't be more specific than that. Okay? You have to think of this as a formalism to be instantiated, okay? So this is the underlying formal model that we have the idea of these predicates. Very often the predicates can have a compact representation. So for output, the predicate can just be, for example, select the input item that has the same key as the output item. Okay, then you don't have to write a separate predicate for every one. And this logical provenance I'm going to show you effectively does that. Okay, people are starting to look blank. Everybody sort of, okay? More or less. And sometimes you can generate those predicates automatically. Okay, but this is going to be a formalism I'm going to use to study the refresh problem. We're going into this good news for academics part of the talk now, where we get to work on fun problems. Okay, yes?
I assume an extreme case of a predicate in one is it came from record 17.
That's the extreme case, and that's absolutely allowed. Yep, find the record on the input that has ID 93624 or whatever. Yep. Yes? It doesn't tell anything about the transformation. That's right. So when I define provenance, I defined it as a mapping from input elements to output elements. We're focusing more on the data than the transformation itself. I mean, we know it went through the transformation. That's partly also, there's these various these various assumptions I've made. One is that we have a static workflow. So we know the transformation. I can tell you that it went through that black one there because that's static. Yep. Okay, and so we can give a natural recursive definition if we want the provenance of an element here all the way at the front. We apply its predicate to get elements here, and then we trace them backwards. Everything I'm going to do is going to have this natural recursive definition of provenance where you go backwards through the provenance. Yes?
If you have as your input perhaps multiple input sources, like the join of multiple operations.
Yeah, so this does, I think, right there, thank you, extends to multiple input sets and output sets. Yeah, you have to have a predicate for each one. You have to have separate predicates for separate inputs. That's the way we model it.
Sure.
Yeah, and that generally is expressive enough.
And I take it that you actually run into the worst case quite a bit, right, if you have aggregation.
Well, a typical group by aggregation, you can just go to the group that it produced. So it's not that bad, right?
Okay.
But sometimes things get tricky if you have joins and you didn't save the join attribute, for example. So think of doing a join on an attribute, but you don't save that in the output. That can actually be kind of tricky to find the provenance in that case. Yeah?
I'm a little confused about one thing. To me, it would be more natural to express the output as a function of the predicate.
The function goes this way. The predicate finds the data. But yes, if you can invert the function, that's more like a tracing procedure. If this is running a function and that function is invertible, then you could just have this backward tracing. The thing is, it's not always invertible.
And then the other thing is you said that if there were multiple inputs, you had a separate predicate for each one. But can an output be a function of multiple inputs at the same time? or is that why?
Yes, it is at the same time, but you have to see an example to see how it works. But if you have multiple inputs, I mean, if they're doing a union or something, it's pretty easy. It depends what they're doing with the multiple inputs. Yeah. We can talk about that a little more offline, but it gets a little hairy.
I take it, I mean, really what you're trying to do is you're just trying to find, hey, what were my inputs if I wanted to reconstruct this value?
We're going to get to that. That's next. You're asking all of you're ahead of me here. Okay, so if you look back in the literature at the rather vast literature of provenance and different ways of expressing it, most of it can be captured with this language. Think of it as a formalism. Okay, so it's going to come to what you were talking about, but now let's talk about the refresh problem. So the refresh problem says I have some output elements and my input might have changed. I don't want to run the whole workflow again, but I want to refresh those particular output elements. And I like the refresh operator because it stresses provenance. It says I need to be able to trace backwards, but I need to also be able to propagate forwards. And actually tracing backwards and getting the data that will propagate forward in the right way sort of tells you you had the right provenance. It's a little hard to explain. So let's look at what we would do with refresh. Let's say that we just want to refresh an element, an output, through one processing node. Okay? So we have our input, we have our output, and we want to take OI, whatever it is, 04, and we say, I want to find out whether the value of 04 has changed. Okay? So we've got a new input. I want to see if the value has changed. I'm going to backward trace by applying my predicate associated with my output element, which is PI, to the new input. Okay? That's what I'm going to do. And then I'm going to propagate that new input. So that's going to give me I star, some subset of the input. Okay? So I apply my predicate. I get a subset of the input. I'm going to send that input through the processing node, and that's going to give me my refreshed value. Okay? That's pretty simple, very straightforward. Example, I am doing my aggregation. I have a prediction that my beret is going to have high sales. Here's my predicate. My predicate says the provenance of my beret prediction is going to be all input items that are berets. So this is your first example of a provenance predicate. Pretty simple, right? Okay? And now I've updated my input, and I want to refresh that. So I apply my predicate, item equals beret, to the new input. That's going to get me all the new values for beret. I send it through, and I might have a new prediction. Okay? That's how a refresh works. Very simple. Okay? The question is, does it always work? Actually, it doesn't always work. You have to have certain properties for it to work, period. And I'm going to tell you those, but we're not going to go through them in any detail. The other is, does it make sense? It actually does generally make sense. But it depends on certain properties of the processing nodes and the provenance itself. We can sort of generalize the whole idea to go through an entire workflow. So we have output here, and we want to go all the way back to our original inputs, which might have changed. So I do recursive backward tracing, and then I send it all the way through the entire workflow. Okay? And then the question is, does this work? And does it make sense? And is it efficient? Actually, maybe it's not efficient. I'm not going to answer those questions for you today entirely. I can refer you to a paper. It again depends on properties of the workflow. I'm going to give you just one second. I'm going to give you an example where it doesn't work. Then I'm going to state the properties for you, and then we're going to leave this topic. Yeah?
How do you deal with a case where there is something missing in the output data?
Yeah. Yeah, there's been a small amount of work in that area. I think it's a great area. The question is, I look at my output and I expect something to have been there and it's not. And I want to ask, why is this not there? There's been maybe 1 or 2 papers on that topic in a very restricted setting of relational queries. I think it's a great topic. I haven't worked on it. Yeah. Okay, so let me just give you an example of where this refresh does not work, and then I'm going to tell you the properties that you need for it to work. So it's not going to work for every workflow. So let's suppose that we have a very small sales workflow here. We have people who live in a city, and they sell things in euros. We convert euros to dollars, and then we sum up for the cities. So we have these 2 people who sold Amélie and Pierre from Paris. Each sold 10 euros. We convert it to dollars at the 1.3 rate. And then we do a sum. Let me add the provenance predicates here. We always have to remember our predicates. So the first tuple has the predicate person equals Amélie. So that predicate applied to this first table will give us the first tuple, and that'll set up the provenance from the first tuple in the first table to the first one in the second table. Okay? And similarly, we've got our predicate Pierre here to find the provenance of this tuple back in the original data. Okay, now I'm going to sum those, and I see that for Paris I sold $26, and the provenance predicate here, pretty simple, city equals Paris. So this Paris tuple, to find its provenance, I go back here and I do select city equals Paris. Okay, so now you can see how these predicates work. It's all pretty simple. Okay, so now I've updated my data. So Amelie went out and sold some more things, and I know my data's been updated, so I decide to refresh my output tuple. So I'm going to follow my procedure of backward tracing and forward propagation. So I trace backwards by applying my city equals Paris predicate, and I get those two tuples there. Okay? I trace those backwards. So the first one's going to give me Amelie. The second one's going to give me Pierre. Okay? So I've got these now. And then I'm ready to forward propagate. So I just send those two tuples, only those, through the workflow that updates the sales here, this 26 value, and it updates the total, and everything's great. Okay, here's a simple example where it doesn't work. Let's suppose now that we have a new salesperson, Marie. Marie's a good salesperson, and so we have new data. We want to refresh our output, so we ask to refresh the tuple. We follow the provenance predicates, and we get the two tuples for Amelie and Pierre. You can see what's going to happen. We follow those provenance predicates, and we get the first two tuples here. We send those through the workflow, and nothing changed. Okay, so the problem is that we missed this third tuple here. And probably a lot of you are thinking of all kinds of solutions to this problem, and there are all kinds of solutions to this problem. What we focused on is addressing when this problem doesn't arise, actually. Okay? So what we should have done here is we should have added Marie, and then we would have gotten the right answer. Okay, so I'm just going to tell you with screen snapshots from our paper, here are the properties you need in order to guarantee that refresh works. And that's pretty much what we studied for that problem, was how to do it efficiently when you can do it, and the properties you need in order to do it. Okay? All right, we built a system based on this. I'll describe the system very briefly. We built it using the SQLite library. We put our data in there. We had our workflow in there. We stored provenance predicates. I actually brushed under the rug that you need predicates that go in the other direction too, actually. Didn't tell you about that, but it's not adding a huge amount. And then the user can create tables. The user creates workflows by defining transformations. Currently, the system has SQL transformations or Python transformations. You can backward trace, you can forward trace, you can refresh. And that's the basic Panda version 1. Okay. That's part 1. I'm now going to go into part 2, logical provenance. Any question about the predicates? Okay. If you're interested in those properties, you can get the slides or look at the paper. Okay, logical provenance is actually the most recent work we've done. Logical provenance, instead of specifying the provenance at the data element level, specifies it at the transformation level, so it's much more compact. Okay, just one specification for the transformation, no matter how big the data is. And it turns out that provenance specification is often equivalent to specifying it at the data level. So underneath the model is still this mapping from input to outputs, but we're going to specify it at a logical level. Okay? And physical provenance, of course, would be specified at the data element level. So what we're going to use for our logical provenance specification language is what we call attribute mappings and filters. And it's pretty simple stuff and pretty effective, as I said. Okay, so let me explain what an attribute mapping is. And we've seen cases already, you might have even thought of this already, where we could have used this mapping between input and output attributes to specify our provenance. Okay, so let's say, again, we have our input set and we have our output set, and let's say that we have an attribute, and they don't have to be relational as long as they have some, record sort of fields or something that we can identify. So this one has an attribute A, this one has an attribute B. An attribute mapping says there is a correspondence between A and B. Usually it's an equality correspondence, but it doesn't have to be. Simple case, I preserve the key, right? That's a very simple case, but very, very common. So we want some way to capture that, even if, it's not going to happen in all of our processing nodes. If it happens in any, we'd like to make that be an extremely simple case. So what this mapping says is that, in this sort of informal, if we have an output element O, then the data that contributes to O is the data in the input that has an A value that is equal to O's B value. Okay, so if I have a bunch of hats in the output, then it came from all the hats in the input, for example. Okay, very straightforward. More generally, if you have an attribute mapping, what it says, if you like formal stuff, is for every possible value of X in the B's, if you take the A values that have the A's that have that X value, and you take that portion of the input and you send it through the processing node, that will contain actually the output that has X for its B value. Kind of think of it as partition. Take the input, partition it by its A values, send those things separately, and you'll get the output elements whose B values are the same as the A values. Okay, that's the way to think of it. Okay, and I've specified that just all I wrote was this. I have no predicates, no pointers, no anything. Okay. So, and a simple example, if we have our customer an item, the probability of buying that item, we send it through the aggregator. This is from my original example. Then we have an attribute mapping that the output items, this is aggregated on items now, go to the input items. Very common if you have a SQL query with a group by, and the group by attributes are in your select clause, then those group by attributes are your attribute mappings. Works beautifully. Okay? So we've proven various properties of these mappings. You can merge multiple mappings. You can split mappings. They're transitive, all kinds of nice things like that. The worst case, remember we had that worst case provenance predicate P equals true? The worst case here is your attribute mapping is empty. That says that my partition is the whole input and output. Any element in the output, its provenance is the entire input. That's what we're always degenerating to with all of these formalisms. Now, we can actually generalize these attribute mappings to more data log-like rules. This would say, the output item attribute here came from the input item attribute, for example. Or we could add predicates. We could say, okay, I have two outputs, output 1 and output 2. Output 1 came from the input item whose probability was greater than 0.95 and probability was less than 0.95. You can also have functions. You can say, I map a name in one to the capitalization of the name in the other. So actually attribute mappings can be pretty nicely extended to be fairly powerful. This is the only other sticky note I'm going to say we actually never got to that particular aspect of it, but I think it's doable. Okay, so that's attribute mappings. That's half of our logical provenance specification. The other half is predicates, and predicates are really simple. But this makes our language fairly powerful when we add filters. Filter just says, basically, I'm going to apply a filter in this processing node, and none of the data that fails the filter is going to come out. What it says is that if I apply a filter, if I have a predicate F, a filter, and I apply it to the input, the output, I'm not going to lose anything in my output. Okay? And let me just give you a simple example. So if I have, for example, person, country, sales, and I'm taking out the French sales, I only am keeping the ones that are from France, then the predicate country equals France is part of the provenance. It tells me that my output is all going to come from the French input. So that would be a predicate there. Okay? And I can add to this particular example also an attribute mapping from person to person, right? So if I add an attribute mapping, what that is telling me is now, this is I've combined those two things. It says when I want to find the provenance of an output element, I apply the attribute mapping to the input and I apply the filter. Okay? So in this case, my attribute mapping is people, and the important thing is that if I want to find the output of the provenance of a person, I'm going to find that same person in here, and I'm going to apply the filter that country equals France. Trust me, this all works, and it's actually quite simple. Okay? So the general case of logical provenance is that I have a set of attribute mappings and a set of filters, and I describe that at the transformation level, and I don't do anything at the data level. Okay? And so we've, again, developed a theory. We've developed a theory of when these provenance is correct, when it's precise, the minimal provenance using these descriptions. I'm not going to go into that. You start, again, with the transformation, the processing nodes, and then you extend to the workflows recursively. One thing that's interesting is that in the case of SQL, For most SQL, you can automatically generate the logical provenance specifications, and they are correct and they are minimal. And by minimal, I mean they capture the smallest amount of provenance in the input. So you've got your output, your transformation with SQL, you've got your output. I can give you a specification that will give me the smallest relevant input. Okay? Yeah? Yeah, but the predicate in the first one was per element. The filter is for the whole transformation, so that's a big difference. Yep. And let me just mention just one more thing. When we implemented the logical provenance, so we did a second version of the system based on logical provenance. Really the most interesting thing in the implementation is if you have a big workflow with these logical provenance specifications at each node, the basic idea is you would trace backwards, step by step using those specifications. But what you can actually do is sometimes, not always, you can merge specifications from two processing nodes, and you can skip the intermediate data. So I could just take I have two processing nodes that are adjacent to each other. I have specifications for each. I can just put those together and make it as if it's logically one transformation and ignore the intermediate data. And that's a nice property, and that was sort of the most interesting thing we did in the implementation. So let me just mention version 2 of the system. So version 2 now, instead of the predicates down here, we have our attribute mappings. They can be inferred automatically for some types of transformations, or the user has to specify them if it's an opaque transformation. And we have the filters, and then we also built a graphical user interface for version 2, but otherwise it supports the same operations. Okay? Questions about logical provenance? Yes? Yeah, so I mean, all of these things you could try to generate by observing the behavior, and there has been a fair amount of work on that. If you're generating a filter, it might not be a hard guarantee, but on the other hand, one thing about provenance is sometimes you don't need everything to be exact. It can be approximate. We've mostly worked in the exact world, but if you're willing to be approximate, then you can do that. You can observe and start, getting heuristics about the provenance. Okay, now let's go to the most narrow topic, which is what we call generalized map and reduce workflows. We're still in the same picture of a data-oriented workflow, but now we're going to ask the question, what if every transformation was known to be either a map function or a reduce function? So now we have very specific properties of how each processing node is going to behave, and with these very specific properties, it can be easier for us to define provenance, capture provenance, and exploit it. And in fact, you can write an automatic wrapper on top of Hadoop that will capture provenance when you know these are map and reduce functions with very little intervention of the person who's writing the job, and it doesn't interfere with the behavior of Hadoop. So this is really, again, very narrow, and it was one student, 1 year project or less. So let's look at map and reduce functions. So a map function, this is my definition of a map function, and I'll just say right now I'm assuming map functions that don't have strange side effects or store things. A map function says if I have M as my processing node, then the output of that processing node M is the union of applying it to one element at a time. Okay? That's the definition of a map function. Everybody good with that? So the provenance is pretty easy. The provenance of an output is the single element such that that output was produced when I applied the map function to that element. Okay? Very pure definition. Everything works. Reduce function is the same basic idea, except you're doing this grouping or this partitioning. So I'm going to define a reduce function to be a processing node R such that I can separately apply R to each partition based on a partition key. Okay? And that's the that's the idea of the reduce function. So as a definition of the reduce function, I partition on this reduce key. I have n partitions. I apply R to each one separately. And then I give basically the same definition. The provenance of an output element is the partition that produced that output element. Okay? And again, I'm assuming no storage or side effects here. Okay. So now I've told you what the provenance is for, I've told you how you find the provenance for a map function or for a reduce function. Okay, I've defined it for you. And again, the same old recursive definition. If you want provenance of an output element, you go one step at a time to get the provenance of the input. Okay, so if we have a workflow that has a set of inputs and then we have an output element, let's say that we apply our definition and the provenance gives us these input subsets I1 through IN. One property that we would like, and some of you may see there's a relationship, though not exactly to what we want to happen in refresh. One property we'd like is if I use these intuitive definitions of provenance for map functions and reduce functions, okay, I do a backward trace through using those absolutely intuitive definitions. If I get my input and I run it through the workflow, I sure hope I get my output, right? That should be a good thing. If I don't get my output from following the natural provenance definition, something's probably not great, okay? Actually, it usually holds, but not always. So following the exact intuitive definition doesn't always work. And this kind of does some of the sort of fun, interesting, academic-oriented stuff that you can do with provenance. So I'm going to give you an example, and then I'm going to, again, give you the properties that a workflow needs to satisfy in order to work. Okay, so in this example, we're going to be analyzing tweets. So people are going to be posting Twitter. They're going to be tweeting about movies. We're going to infer their ranking or rating of their rating of a movie based on their tweet. We're going to summarize those into median ratings for movies, and then strangely, we're going to count up our movies per rating. Okay, this is pretty strange, but I needed to do it for this not to work. And you'll see what I actually needed was this series of non-monotonic and one-many transformations to make this procedure fail, actually. So most of the time, tracing back with the simple definition works, but here's an example where it doesn't. Okay, so this is a map function for the scanning. It's two reduce functions, map, reduce, reduce, and gives us our output. So let's just look at how it works. So let's say that our input is a bunch of these. This will tell you approximately when we did this work. When did Twilight and Avatar come out? Like 2 or 3 years ago, I guess. Okay, so we tweet about these movies. Someone says Avatar was great, they hated Twilight, and so on. We're going to take those tweets and we're going to turn them into ratings somehow. So Avatar got an 8, Twilight got a 0, I hated it, and so on. All right? Everybody with me? I'm going to take the median for each one. So for Avatar, the median rating was 7 because I had an 8, 7, and 4. And for Twilight, I had a 0, 2, and a 9, so I get a 2. Okay? And so that tells me, now my last thing is to say how many movies have each median. I know this is weird. 2 movies, median of 2, I had 1 movie. Median of 7, I had 1 movie. Okay, you need this double aggregation to make things fail, as a matter of fact. Okay, so, but actually right now with this data, things are fine. If I trace backwards using my definitions of map for provenance for map and reduce functions, this median of 2 is going to go back to Twilight, because that's the one that has a median of 2. It's going to go back to those 3 Twilight records. It's going to go back to the Twilight tweets. And remember, what I wanted to happen was after I trace back, using my formal definitions, and I then apply just to those, I apply my transformation, my workflow to just those, I want to get my output. That's the property I want, okay? So I send these through, I send these through and I will get the same output. So everything is good in this case, all right? So just again to emphasize, I've got a simple definition of provenance for map and reduce functions, the very natural definition. I use that definition to go backwards through my map and reduce functions. I get to the front, I get a subset of the input, and I want, if I just ran that subset through, to get my output. All right, so here's an example where it doesn't work. This says, I've changed my tweets, and now I have one that's about both movies. It says, I enjoyed Avatar and Twilight too. Okay? So this is going to be a one-many, but one-many is fine for map functions. Map functions don't have to be one-to-one. And one-many is actually crucial to this counterexample. Okay, so now I actually get these ratings here, okay, from this. But now we see that this one here is generating 2 ratings right there, Avatar and Twilight. Now I get my medians, they're the same medians, okay? And I get my same count at the end. All right, so now I'm going to trace backwards using the definitions of the map and reduce provenance. Here we go. I'm going to trace this one, the median of 7. It's going to give me Avatar. Avatar is going to give me these 3. Those are going to give me these 3. Okay, so now I've traced back using the intuitive definition. Now what happens if I push those through? The problem is, well, let me just start here. If I push these three through, I get avatar 8, avatar 7. I get this little twilight couple here, right? And avatar 4, I designed this data so that now twilight is going to have a 7 as its median, and I get a 2 here. Okay? So, didn't work. Now, what are the properties that caused it not to work? It's pretty esoteric, to tell you the truth. The first one is a one-many function. That's key to the counterexample. If it were one-one function, I don't have the problem. The second one is a non-monotonic reduce function. And the third one is also a non-monotonic reduce function. Believe it or not, you need to have one-many followed by non-monotonic followed by non-monotonic for it not to work. And we've proven that. So there you go. There's the theorem. But you don't need to read that now. Anyway, otherwise it'll work. If you have only one non-monotonic or if you don't have a one-many, you're in good shape. Okay, so we built a system based on this completely separate system. We built it as an extension to Hadoop. It's an academic proof of concept. It was mostly based on backward tracing. We didn't tune it for forward tracing or for refresh. You can submit a Hadoop job. It will automatically wrap it. It will generate default IDs. And we can have user-defined schemes. We can add indexing. I'm getting late on time, so I'm not going to talk about it in great detail. We did some preliminary performance experiments. We had roughly 50% time overhead on a 500 gigabyte workflow, and it takes a second to trace things. For demos, the most fun, I would say, is actually pig scripts. So what we can do is take a pig script that generates a pretty complex map reduce workflow, and it will automatically capture provenance for that. And that has a bit of a wow factor, I would say, for people. So this was a separate project, but I think maybe in some sense the most practical. All right. So I'm just going to spend a couple minutes on follow-on work, and then I'm done. Why don't I just do that and then see if there are any more questions? Okay. So first of all, I actually, some of you probably observed, I sort of showed you 3 separate things, and they have some relationships to each other that we haven't even completely understood, frankly. Predicates are the most general logical provenance, less so these generalized map and reduce workflows the least. So that's their relationship. We haven't really unified them. Second, we used a pretty specific provenance model in a way. The underlying model was very fine-grained. Data item to data item. We also focused, as someone asked, on data provenance, not on process provenance. So we're really focusing not on the processing nodes and what nodes a data item passed through, but rather the relationship between the data itself. And when you have dynamic workflows, what nodes data pass through becomes much more important. And I also didn't do anything with time and versioning. I think that's actually pretty important too. For all of these, you'd have to extend capture, tracing, and propagation. I discussed ad hoc queries. I actually think this would be a really fun area to work in. I don't know, how, again, there's this sort of common denominator. Whether you can get a provenance query language that satisfies lots of people, I don't know, but it seems like fun to design a language that queries data together with provenance and you optimize it in interesting ways. I also think if you want to query provenance and you know what you want to query before you run the workflow, then you can actually tailor what provenance you capture to the queries that you want to answer about it. So that seems like a kind of fun area too. Then there's also, I think, a very practical problem. We worked on this a little bit about optimizing what you do when you're capturing provenance and exploiting provenance. And the whole question of eager versus lazy, do I want to do the work as I send the data through the workflow, or do I want to do the work when I need to trace provenance, is actually a pretty hard question. There's space-time trade-offs. It's the query update trade-offs, the usual type of trade-offs, but it also depends on what kind of nodes you have. So I gave the example where deduplication, it's very easy to capture provenance eagerly and very hard to capture it lazily, whereas aggregation, a simple aggregator, if you do aggregation, you're doing a big, say, group by aggregation, it's you're keeping the group by attributes, it's pointless to, in your output, capture all the pointers back to all the elements that generated the output. It's a huge waste of space. So you really don't want to do eager in that case. So different nodes have different needs, let's say. There's the question of whether you want to retain intermediate data when you're operating on provenance. And I just gave a brief discussion of where in the logical provenance we have a mechanism for, sort of with formal foundations, eliminating keeping intermediate data for provenance tracing. In the extreme case, when you think about whether you want to keep intermediate data, you run the workflow once. So you have all your inputs, you run it once, you get all your outputs, nothing's ever going to change, and you're going to do a huge amount of provenance tracing. Then you should do all your work up front. You should throw away the intermediate data sets, capture your mappings from the original input to the output, and you're done. Okay, so just decide. There's a big area of theoretical decision problems here, actually, as well as system issues. Okay, related work, huge, many decades of work in provenance, tons and tons. That kind of goes back to my original opinion that the problem will never be solved, but there's a whole bunch of fun research to do. And I'm finished. So thank you. Questions? Yeah.
In your lineage predicates, usually what you mentioned was conjunctions.
In the predicates, I mostly mentioned.
There were usually only conjunctions.
Oh, conjunctions. No, you could have disjunctive predicates without a problem, I think.
Okay.
Yeah.
Do they arise naturally? Like some birth fruit, do they arise naturally?
I could come up with cases where it's more like if you want to identify a group of things. If for some reason I'm computing my hats and shirts together into one prediction, then it might be, it equals hat or equals shirt. That would be an example. Yeah. So I think they can arise fairly naturally. Yeah.
So you mentioned that you don't think that there's a general solution to the problem because the common denominator is so small.
Right.
Can you give kind of a couple of examples where some big provenance needs here doesn't intersect with some big provenance needs there? Maybe just getting one through for me in the example in the discussion.
Oh, how do I justify my claim that the common denominator is small? I can't justify it from a technical point of view. I can more justify it by just saying when I talk to people, everybody wants something different. There's just some tweak that makes to their problem that makes this not quite the right solution. I don't have a mental image of actually a Venn diagram with small intersections, even though I claim that. I more have an image of here's a solution, oops, doesn't work for this. Here's a solution, oops, doesn't work for that. Where all of those oops are sort of different reasons. I know that's kind of a fluffy answer. That's my gut feeling.
Since we have you on camera, would you be willing to put up $1 for anyone who tried to prove your own?
Who makes a general purpose provenance solution? Oh, more than $1. I'll buy them lunch, dinner. Yeah. Other questions? Okay. Thank you.